My name is Trevor Hrynyk. I'm an assistant professor at the University of Waterloo. But I should also really take a minute here to acknowledge my prior MASC student, Reza, who's really, the intention was for him to come give this presentation. This is entirely, or effectively, his work. Unfortunately, visa issues, he couldn't make this trip. So, yeah, what I'm going to talk about today is a piece of what Reza had been working on over his time working with me at the University of Waterloo. And specifically, he was doing some finite element simulations to see, or I guess you could say to assess the applicability of an existing modeling method for certain types of punching-related analysis conditions we hadn't looked at before. And specifically, we've named this RC flat plates subjected to non-uniform connection stresses, which you can make a case they're always subjected to non-uniform connection stresses. But here we're talking about non-idealized slab-column connections that really accentuate eccentricity or having very large shear stresses on one side of the column or something like that, other than bending. Okay, so just due to gravity loading. RC flat plates, I think we're all quite familiar with what we're talking about here, but obviously a very popular option in North America and much of the world for a number of reasons. Very flexible, very good for construction, cost effective. Unfortunately, kind of the Achilles heel is they're more susceptible to punching, right? That's kind of their primary drawback if you were to think of only a few. So the motivation in terms of the research we're doing here is we wanted to look at analyzing slab column connection types that are a little more representative of what's actually used in design. So not exclusively concentrically loaded slab column connections where you have uniform reinforcement in the two directions. You have a square column or circular column subjected to perfect gravity load. We wanted to look at other cases where you might get something a little more representative of what's going on in real world construction. And the second motivation here was to assess whether or not an existing modeling procedure that we've been using for several years would actually work for these cases. Because we've done lots of the other type of analyses, idealized, concentrically loaded punching type specimens, and it works great. But you kind of ask the question, who cares? Because those connections don't really exist. So in this presentation, we're going to look at the feasibility of using what I'm calling a lower cost shell element based finite element analysis procedure to estimate the punching performance of RC flat plate connections. And for brevity, performance in this case is largely strength, but obviously you could use it to look at a lot of different things. And of course, the important points here are we're looking at connection specimens that are not idealized. And we're going to contrast this just very briefly with some prior analysis results we got using the exact same modeling procedure, the exact same techniques, material models, everything the same, but for idealized specimens, and see whether or not it's as capable, it has more deficiencies, or whatever the case may be. So briefly, I'll talk about the procedure we're using here, a very quick overview. We used 4 test series for, I guess, validation or verification in this case. Actually, the same one Graham referred to, Hawkins, 1971. Oliveira Ale had a very nice test series, or several test series done in 2004, and 2 test series coming out of EPFL, of which Hawkins Ale was the lead author on both of those. Okay, so the shell-based reinforced concrete finite element analysis procedure we're talking about here it's actually vector 4. It's one of a series of procedures. But really the motivation behind using this type of procedure, it's broadly applicable. And because it's employing shells instead of three-dimensional solid type elements, you can do these analyses pretty quickly. So these were just some relatively recent prior applications where we use this type of thing. And you can see it's kind of broad. So non-planar shear walls, obviously the topic of this would be maybe you have some type of irregular flat plate that there's something atypical about it that you want to employ a nonlinear analysis procedure to get some more insight on it. And then some prior work we were involved in involving reinforced concrete storage silos, which ironically enough are actually governed by punching, even though this is not a building type application. So the way it works, It employs a layered thick shell finite element, so this is kind of like a fiber or layered model. It's based on simplifying assumptions, the main one being plane sections remain plane, which everyone's pretty comfortable with. A secondary assumption which is used, which is actually pretty critical to how it performs, is how the net shear strain is distributed through the thickness of the section. So we assumed a parabolic variation of through thickness shear strain, and this is what would happen with a linear elastic model. This would agree with that. We actually found it provides a reasonable approximation of what's going on for nonlinear analysis, at least in terms of ultimate performance. It's a higher order shell element, so it's 9-noded, 42-degree freedom, and it's a thick shell element, so the key part there is it can account for through thickness shear strains, which is critical, obviously, to punching. In terms of material modeling, it employs disturbed stress field model, which is an extension of modified compression field theory. So this is a smear crack modeling approach, and it's something of a hybrid rotating fixed smeared crack model. Inherent to it, without really a whole lot of modeling specification, it accounts for compression softening, tension stiffening, and a key feature is really what it does at crack surfaces. So it does a specific examination of what's going on the crack, and this circled point I have here on the bottom, the fact that it accounts for shear slip along crack surfaces, this is really the primary differentiator between, there's several things, but I would say this is the main one differentiating DSFM from modified compression field theory. Graphically, what this looks like, just very quickly. So these are kind of a pictorial view of key aspects of response. So the plot on the top left there is kind of showing what we're doing for post-cracking tension response of reinforced concrete. So even after concrete cracks as a result of tension stiffening, we're still able to carry some tensile stresses between crack locations in concrete, so we account for that. In the bottom left, we're showing the degradation of compression resistance as a result of compression softening. So when you have lateral tension inducing cracks, our concrete's ability to resist principal compression will deteriorate. And on the left side of this, it's just a very simplified overview of what this crack examination looks like. So if you'd imagine at a crack surface on one side, we have sound crack concrete, and you have a set of stresses in concrete and reinforcement on that. And if you were to examine on the crack surface, you have an entirely different set of stresses because we're at a crack, but those things equilibrate each other. Okay, so this is all kind of inherent to the model. From a user's perspective, all of this is going on behind the scenes. In terms of what we did on the user side, we didn't do a lot. So we specified very basic input properties, material properties. So for concrete, the two properties we specified was F prime C and the aggregate size. Everything else we assume based on typical assumptions. And steel, we specified stiffness, yield strength, and ultimate strength, right? So in cases where we had test data actually showing what the stress strain response of the steel was, we would kind of utilize that. We used in all cases what we refer to as default supplemental material models. So there's a lot of models that disturbed stress field model doesn't account for, things like confinement, Poisson effect, dilatation. These were never part of that original model. So these are kind of supplemental models that are added on. We didn't parametrically define these. These were just set based on what we always do with these models. Okay, and then an important point here at the end, we made no attempt to calibrate our model. Okay, so we use the exact same material models analysis parameters I've always used with this program for the last 15 years. Okay, now relevant to punching specifically, there is one modification that was made in our prior work when we looked at whether or not this type of procedure would work for that application. And that was to deal with disturbed regions. So when you think of the major assumptions governing what's going on in shell type analyses, they're actually really bad for punching. They're the exact opposite of what's going on in that critical region. So plane sections remain plane, probably not at that critical region, right? It's too much of a disturbed region going on. Another assumption built into shells is we tend to neglect out-of-plane confinement, right? There is no out-of-plane degrees of freedom, so there's no clamping that we can account for in the analysis procedure. And unfortunately, in punching type applications, we often have shear cracks right at that column, slab column intersection. So there's a potential for a lot of clamping and confinement going on. So both of these have been overcome using what we call a shear strain suppression procedure. And basically all it is within a distance of h around any large out-of-plane restraint or load, we suppress some of that out-of-plane shear strain, okay? And this was part of a prior study, and we showed that it worked pretty well. And we don't fully suppress it. It's a linear variation of suppression. So when you're directly at the column face, it's fully suppressed, and as you move away a distance h away from that column face, it's a linear reduction to how much suppression. So once you get h away from the column, there's no suppression of these through thickness shear strains. Now, I don't want to spend a lot of time on this, but as I said before, we did use this exact same procedure to analyze what I'm calling idealized connections. So these are the types of, the bulk of what we have in the literature for punching tests. So these are isolated interior columns where the reinforcement is uniform in the two planar directions. It's on a square column or a circular column, and it's under perfectly uniform gravity load and supported somehow around the perimeter. So everything's nice and concentric. When we looked at this everything nice and concentric case, specifically we looked at a few cases from EPFL, a total of 21 slabs, and this was actually a really nice test for us because we were able to use one mesh for all 21 slabs. So common mesh, common material models, common everything. The procedure worked really well. In fact, it worked almost as well as what we would get using a more detailed, solid three-dimensional modeling procedure. So my apologies, the plot's kind of hard to see, but if you see that red dash line, that's using the exact same material models and analysis parameters with solid elements versus that very light blue line using everything the same, except we did it with a thick shell analysis procedure. And obviously the big change there between the two is one took hours to run, the other one took minutes to run, right? And that's really the motivation behind why you might want to simplify your life a little bit. When you looked at all 21 slabs of that study, the results were arguably pretty good. So, you know, mean right on the money with about 10% variation for both solids and shells. So the conclusion from that was we can do things with a shell about as well as we can do them with a solid element modeling procedure. Now, the focus of this one really was to look at other non-idealized type of connections and see if we can get that same level of precision and accuracy, because we hadn't really tried it before. So, as I mentioned before, we looked at 4 test series, some common elements of them. None of them contained out-of-plane shear reinforcement. Thickness range from 130 to 250 millimeters. Reinforcement ratio from 0.3 to 1.6%. But really, the big key difference here is rho X and rho Y was often not the same. So we had different planar reinforcement ratios, which causes funny things to occur at the connection. Varying column aspect ratio ranging from 1 to 5, and column aspect ratio being that ratio of long side to short side. And then several of them had either 2 or 4 edge loading. So they were punching type specimens, but often they would load them on only one edge in a manner to try to accentuate stresses on certain sides of the column. Okay, it caused non-uniform stress, shear stress development around it. This was the typical modeling approach. So these were all interior isolated connections, and in all cases we analyzed a quarter slab mesh just to make life easy. All analyses were done that way. All analyses were done with 20 concrete layers. All were done in displacement controlled analysis, and all had the exact same material models and analysis parameters. There was some, mild mesh sensitivity done, but this was never done comparing with experimental data. It was only done to see when do the numerical results converge to an answer. So it was independent of the results, experimental results. This didn't necessarily mean the mesh we picked was a good one to get good agreement. All it showed is that once we went from very coarse to less coarse to marginally coarse, we got about the same results as what we'd go if we kept making that shell element mesh finer. Okay, so we ended up selecting that one, at least in the case of Sagaseta AL 2011, that's highlighted there in red. Okay, so very quickly I want to go through these. The first one we looked at was Hawkins Ale 1971, and admittedly we did the worst on this one. This one was not that well done. We really struggled with it. Just to give you an overview of what it involved, there were 9 slab column specimens. They were loaded under perimeter loading, That varied. Sometimes it was 2 edges loaded, sometimes it was 4 edges loaded. It had varying reinforcement ratios, and all the slabs were 150 millimeters thick. And the primary variable in the research was column aspect ratio. So they had different rectangular column sizes. They only reported load deflection behavior for 3 of the 9 specimens in the research. So we analyzed all 9 for strength, but I can only show you results from 3 of 9 here in terms of load deflection. And you can see in a couple of them, we're kind of capturing what's going on, H3 and H7. In H1, this was probably one of the worst specimens out of all 35 we analyzed. We're way off the mark. In fact, H1 was reported to be governed by a lot of yielding in the flexural reinforcement. We did predict some yielding, but immediately after we had kind of a flexure-induced punching is what came out of the model. Nevertheless, when you look at all 9 of these, we had a computed to experimentally reported mean ratio of 0.88 and about 10% coefficient of variation. If we walk down the line and take a look at Oliveira, it's much the same. They had more specimens, 15 specimens. The primary variable was column aspect ratio, but they also varied the loading. So they had a series where they loaded the full perimeter, a series where they loaded 2 sides, and a series where they loaded the other 2 sides. So it kind of induced different stress conditions around the column. And again, this shows our meshing approach for each of those different cases. And here's the results of all 15. I'm not going to expect you to look at these things critically and spend a lot of time on it, but you can see there were hits and misses. So in the L series on top, we were more or less capturing what's going on. And just to give you an idea, as you go from the left to the right, your column's becoming more rectangular. As you go from top to bottom, it's changing the loading conditions on this slab. All right, so in the A series, it seemed to be okay. The B series, we were stiff, but the strength was okay. In the C series, I think we really missed the mark. So you can see the dashed lines, which is experimental stuff. As the column's getting bigger and more rectangular, they're getting a lot of strength gain. Numerically, we didn't capture that. In fact, we kind of hit a plateau where making the column longer wasn't really increasing strength because we were estimating these punching failures to occur on the short side of that rectangular column. When you look at these numerical results a little closer, in fact, on the top 4 here, what I'm showing here is a set of numerical results for a slab column connection with an aspect ratio of 1. You can see the principal out-of-plane shear strains surrounding that column are as you would expect. They're around the column, nice and smeared around the perimeter. As it becomes more rectangular, you can see it kind of localizes to an edge. And that's why we're getting those premature punching failures. Okay, and then very quickly, the last series I want to talk about. This is actually 2 series. We lumped them together because they were by the same authors. Hawkins Ale, these were slabs tested at EPFL with Aurelio Mattoni's group. And the 2 series were focused on different things, but they kind of produced the same non-uniform stress conditions. So one series was on changing column rectangularity, and the other series was largely focused on non-uniform in-plane reinforcement ratios, so having lots of reinforcement in the X and less in the Y or vice versa. These slabs were a little bit thicker. They were 250 millimeters thick. So we probably did the best on these, which is not surprising because we've done very well in terms of estimating what's going on in the EPFL slabs before. And you can see in this case, with a couple of exceptions, we seem to capture what's going on pretty well. So there's these 2 in the middle on the top, PT31, PT32. A lot of people have analyzed these slabs, and no one really does well with them. They have a very high-strength concrete. And I don't know if that's the source or what the source is there, but it seems to be that this procedure is in agreement with how others have done. And we're not capturing those very well, but the rest we did okay, I think, in terms of capturing strength, stiffness, and response. When you take a look at these things in all, Hawkins, Oliveira, Sagaceta, Series 1, Series 2, you can see none of them were horrifically bad. Hawkins was the worst. But they all had reasonable coefficients of variation, and they seemed to provide estimates that were in line with what was observed experimentally. When you look at the total set, it had a calculated to experimental ratio of 0.94 for the mean, and 13% coefficient of variation, which is not as good as what we got before with idealized slabs, which was right on the money with a mean of 1 and 9% variation, but not horrific. And so the key point here, I'll go to conclude, is that seemingly without recalibrating redeveloping anything, we can use the exact same modeling procedure that we used before and still get some reasonable estimates of response. Okay, and that's really what we were trying to figure out. Admittedly, there were some misses, but I think considering the approach we took, I was very happy with this result. A couple of other points here. I think influences associated with the column rectangularity were not captured as well as I had hoped. But given the data set we looked at, which is the bulk of the data on the topic, I'm not convinced. I don't know where that error is. I don't know if it's something we're doing, if it was a unique intricacy of a certain experiment. That one's going to remain unresolved. And for whatever reason, I'm not going to speculate why, we did better with the EPFL slabs than the others. We've always seemed to capture those things really well. I don't know what the motivation is there. I'm not on the EPFL payroll. It's just worked out that way. Okay. So with that, I'll conclude my presentation. If you have any questions, I will attempt to answer them.